We have just run two different tests, a two-tail test and a one-tail test. In the two-tail test, we failed to reject the null hypothesis that there is no difference in revenue per customer when offered a 5-year full warranty versus a 7-year limited warranty. We failed to reject the null hypothesis. This does not mean that the null hypothesis is true, just that any differences between the distributions of the two populations weren't detectable in our samples, at least to a degree that we could feel confident about. Recall that our confidence level for our tests was 95%. This tells us the chance of a true negative. Our alpha, on the other hand, was 5%, and this tells us the chance of a false positive, or concluding our samples are different when they're not. We might be worried that there is actually a difference, and that our test just couldn't detect it. When we fail to reject the null hypothesis, but the sample distributions are actually different, we call this a type 2 error, or a false negative. To visualize this, let's pretend our samples are different and insert an imagined distribution for our second sample. In this visualization, any sample means drawn from the area highlighted in blue would show up in our test as a type 2 error. A type 1 error occurs when we incorrectly reject a true null hypothesis. The odds of a type 1 error occurring are completely dependent on our alpha. The smaller our alpha, the less chance there is a type 1 error occurring, though this does increase the odds of a type 2 error occurring. So, which is worse, a type 1 or a type 2 error? Ideally, we don't want either types of errors, but in some situations, one may be preferable over the other, and this depends on the specific scenario. For example, imagine you're in a courtroom, and you've been asked to run a hypothesis test. The results of that test will be used to decide if an alleged bank robber is guilty. In this situation, a type 2 error would mean that a guilty person goes free, but a type 1 error would mean an innocent person is punished for a crime they didn't commit. In this scenario, most people tend to say that the type 1 error is a worse consequence, that we'd rather a robber go free than an innocent person go to prison. In this scenario, we might want to assign our test a small alpha. It is important to take into consideration the weight and consequences of each type of error in our testing, as this can help us set up a test to better analyze our scenario. The results of our first test, the two-tail test, might feel disappointing. The actual difference between the means of our samples is quite large, at almost 13%. Over a year, a difference of 13% could be a lot of money. But, using the sample size that we had in our test, we can't be confident this difference actually exists. So what went wrong here? Earlier, we talked about how sample sizes over 30 are generally good enough, though samples of 100 are much better. We're working with a sample size of 750, so shouldn't that be large enough to be confident? Recall that in some situations, we may need much larger sample sizes. One such situation is when there is a low rate of positive cases. If you examine the observations in our data, about 10% of visitors end up purchasing a vacuum. That means our samples are being determined by about 75 individuals. That is a fairly low rate of positive cases. Not only that, but within those 75 or so individuals, there's a lot of variance, with some buying the vacuums for half off and some buying 2 or 3 vacuums at full price. Recall, our average standard deviation is $174. The combination of a low rate of positive cases with this high variance can impact the results of our test. In hindsight, we probably should have looked at the historical conversion rate of our customers when determining our sample size, or looked at industry averages for an estimation of what to expect. If we had expected a high variance and a low conversion rate, we might have known to pull a larger sample. Even though we didn't reject the null hypothesis in this case, the best practice is to still report these findings. Recall that based on the results of the two-tail test, for our next step, we ran a completely different type of test, the one-tail test. We had to update our alternative hypothesis, and we used different samples as well. We changed our test entirely, rather than running the same test again with a new sample of the same size. We did not go back and remove outliers to try and make it significant, or change up the variables, like looking at only results from the United States. Or if our result was close to our alpha, but not quite small enough, we don't want to add just 2 or 3 more observations to see if this changes. These are all examples of what's known as p-hacking, and these actions dramatically increase the chance of a false positive in our tests. Congratulations on completing our Statistics Fundamentals course. You should now feel confident to engage in conversations about statistical concepts and more comfortable to start working with your data science team. You can now understand the fundamental parts that make up the landscape of statistics and are ready to move on to take BETA's more advanced courses. You should have a good grasp on descriptive statistics, inferential statistics, probability, and hypothesis testing. But more importantly, when it is appropriate to use these techniques, as well as the underlying assumptions of these techniques and methods. If you've enjoyed the course, please do share it on LinkedIn. We would love to hear what you think. I hope you'll see us again soon for more content from the Business Intelligence and Data Analysis program. I look forward to seeing you again.